This is Bryan Sousa, and this is my demonstration video for the first Fluent project for the class. And I'm just gonna really quickly explain how I did everything. So first, I gotta pull up geometry in the design modeler and let that load up. Okay. Yep, so first I just go into sketching on the Z-plane. I gotta make the circle for a cylinder. And I like to use a rectangle, and then just dimension everything later. So I just need established dimension for the sides, diameter, and then I go to horizontal actually. Click between the two lines here, and I can establish that horizontal distance and the vertical distance here between the axes and the two sides. Diameter is 1. That should be 50. 25 to center. And yeah, you just put 50 and 25 again. There. So that's your domain. Just go concept, surfaces to sketches. Hit apply there, generate. There's your surface. And we're good to mesh. Okay. So, let's go to meshing here. There we are. So I'm just going to start doing the mesh. I want to put in a method. Oh. Hit this as my geometry. This needs to be, need to go here to triangles. Ah, made a mistake. My bad. Let's just try that again. There we go. Generate just to make sure that the method's working. Yep, it's working. Okay, then I'm going to put in sizing now. I need to select the boundary. Element size, and this is supposed to be 0.02 here? No, 0.05. Right. And this needs to be hard. And then generate again. Yep. I'm going to apply inflation. The entire thing is the geometry. The boundary is a circle. I need first layer thickness. This one's 0.02. 100 layers. And 2.5 growth rate. I'm just going to make sure this works. But it should. Okay. Now to make the mesh even better, I'm going to put this as 0.15 on the element size in the mesh part. I'm probably going to just cut this part to make this video shorter. Okay, we're back. It appears that I can do a whole lot better with the nodes, so I'm just going to really quickly change this to 0.13, and that should be the number required to really refine this mesh all the way. So I'm just going to cut it again from here. Alrighty, back again. I think this mesh is good enough, so I'm going to work with this for the demonstration video. Never forget, create name sections. Inlet in the front, outlet in the back. That's a wall in the circle. And top and bottom need to be symmetry. Alrighty, that should be all. Just need to go back and update. And then we should be good to set it up. If it actually does update. Yeah, there we go. Alrighty. Need to put double precision every time to make sure that the solution is good. Cool, so it's done. Need to go to models. I'm going to show Inviscid first, because it's very easy. So you just make that Inviscid, go to materials, so you can make the density of air 1, for simplicity's sake. Cell zone conditions should be good to go. Yeah, it's good to go. Boundary conditions, very important. Oh. Going to the inlet, and just putting in 10 meters per second here. For reference values, I like to compute from inlet, just to make sure that everything updates right. You need to go to methods and change a couple of things. Go to simple scheme, and Presto should be here. Yep, change that to Presto. Just to make the simulation easy on the computer. I'm gonna go here and do 35 iterations for the initialization. Initialize, and this should converge. Yeah, that's good. Cool. And then I just need to run my calculations at 1,000 iterations. So from here I'm definitely going to cut the video because the calculations can take a bit. So we're just going to be right back here once it's done calculating. Okay, and we're back and the calculations are done. So what I like to do first is go to the results section because I find it easier to pull up all the contours and stuff there, just to make sure that the result is actually good, because otherwise I might just have a terrible solution and not know it. Okay, that's still loading. Cool. Contours are easy, just click that. I don't need to rename it. I need to go to symmetry 1. Let's put velocity, I like 50 contours, apply, and it's just gonna load. Okay, yeah, that looks exactly what we expect. So that's how I did that, and there's your velocity contour. Change this to pressure, and you get your pressure contour. Pretty easy. You can turn that off here, hit streamlines. Start from the inlet, domains is fine. I just need to hit like 250 points. Apply, see how that looks, and oh look, contours. So that's that, and then to pull up the graphs, the plots, you go plots, XY plot. This is fine, you need to go pressure, change this to pressure coefficient, over curve length on the wall, save and plot, boom, there you go. So that's that graph. Same thing for velocity, magnitude over the thing, there's the plot there. And to get the forces, all you need to do is go to reports, forces, hit the wall. In x is one direction, you get drag, which is this. If you change x to 0, y to 1, you get lift. So that's very straightforward. That's it for that. Now what I'm going to do, I'm just going to demonstrate how I did this for the laminar case too. So the only thing that you need to do, go up to here, make it laminar. I'm going to turn energy on just because we are now working in laminar and turbulent. For air, we need to change some of the properties. So in order to make this a laminar flow, it is specified that we need Reynolds number to be 1500. So I'm just going to change the viscosity. So I would take velocity of 10 times the diameter of 1 times the density of 1 divided by that number, 15 with 3, 4 zeros. Okay, then to achieve that, we need a viscosity of 7. Oop, not 16. There we go. You know what? I'm just gonna put a lot of 6s here. That's better. Cool. That should be good enough to go. Everything else shouldn't matter too much. Boundary conditions, the inlets should stay the same. Yep. I'll check this just to make sure that the viscosity, yep, viscosity did indeed change. I'm just going to go back to reference values, hit inlet again to update the values and all. Initialize again. Yeah, it's converging just fine. Cool. And now I'm going to just run the calculations. And again, I'm going to cut the video here because this is going to take, I'm going to show the residuals, but this is going to take a long time, so I'm cutting it here. Okay, we're back. The calculations are finally complete. Let's go back to PST here. Go back to this new data stream so that we can have the simulation here update. We're just going to have to wait a little bit to load. Okay. Let's see here. Yep, it looks a little bit strange, but that's usually how it is when you do the laminar case. Let's check out the velocity. Yeah, it looks a little strange, but in my original making of this, the von Karman vortices are very clear, so I wouldn't worry too much. The process should be the same no matter what. Yeah, you can see some vortices here anyways. That's that, and you already saw the streamline. There it is. And then the plots are literally the same. It's just you go to XY plot. You can even go back to the original here. Safe plot velocity. It's 0 across the whole thing, which is interesting. Pressure coefficient. Ooh. And then forces is the same. I'll just get drag first. And then lift. There. Now I'm going to show how you do rotation. So you just go back to the wall here, double click, and then you go to moving wall, rotational, axis origin on 0, 0 because that's what the circle is, and then this, the speed, negative 20 radians per second is what we'll work with first. That should be all apply. Yep. And then I'm just going to go back to the reference values. Compute from inlet again, just to make sure that it all updated. And then I'll have to run more calculations after initializing. Okay then. Yeah, now I'm just going to go ahead and run the calculations, and I'll cut back here once I'm done with them. Okay, and we're back. The calculations are done for the rotational case here. Let me take these old ones out. Let's go back to PST, see what's changed now that the cylinder is rotating. Okay. So the contour's looking a little bit different, yeah. Alrighty, and yeah, that's the result that I got for this scenario here, so should be good to go. I think at this point I have demonstrated that I know how to do everything for this project, and this video is going to get quite long even with all the cuts. I'll just quickly explain what I would do for the rest of the scenarios. For the negative 40 case, it's pretty obvious what I would do. I'll just go back to the wall, change the speed to negative 40, and rerun the calculations. And for turbulent, I like to use K epsilon, personally. I've tried the Spallerat Almaris, and it doesn't work as well, so I just use K epsilon here. And at first I'll put the wall to 0, because that's what I'm supposed to do. put it to -20, put it to 40. And of course along the way, the XY plot, it's the same thing. You just go pressure coefficient here, on the wall, save and plot, there it is. And then for velocity magnitude, you just save and plot, there it is. So the process is the same. So this should demonstrate sufficiently that I know how to do this project and that I did do it on my own.